One of the things we did also introduce last time was binomial probability. And there was an equation that we learned last time. So if you want to calculate the probability of getting sort of n outcomes, so we're kind of trying to calculate now the probability of n number of outcomes of interest out of m trials, or whatever it might be. And remember that this could be heads, it could be tails, what your interested part is. You've got to read the question carefully to maybe identify that. We said that this is given by the multiplicity, so the number of different ways you could actually have arranged these n number of things coming out of our m trials, times p to the n times 1 minus p to the m minus n. Here, this lowercase p is equal to the probability of the outcome of interest in a single trial. So this could be half and half, but it doesn't have to be. Say for sort of a fair or completely random case. But it doesn't have to. And I think last time we had a weighted coin where heads was 0.7 versus tails being 0.3. Okay? And just remember that this is, of course, our multiplicity equation. So we can plot probability, our binomial probability. So let's say we have 10 flips. We're trying to get sort of n outcomes of interest over here. So out of our 10 flips, going from 0 of them being the kind we want to all 10 being the kind we want, we could plot probability over here, and it would look very discrete. So we know that about, if it was a 50-50 situation, half the time would be the highest probability, and then it would kind of drop off in this sort of curve fashion. And it would look something like this. And if we have sort of even more cases, so this is now probability of sort of n number of positive outcomes. Maybe if we take it up to 100, we know again, if it was sort of equal probability of either, the highest probability sort of at the center, and then again, it would drop off in this sort of curved fashion. And it has sort of this normal distribution. And so basically, this distribution is also called a Gaussian distribution. Like I said, or normal. And basically, the Gaussian distribution is an approximation of binomial case when m gets very large. And you can just approximate it as this nice sort of smooth curve. And so we have an equation for probability for the Gaussian distribution. So for our Gaussian distribution, the function that describes our smooth curve here, probability of x is equal to 1 over the square root of 2 pi times sigma. EXP here is notation for e raised to the, if anyone is unfamiliar with that, e to the whatever. If you ever didn't have a calculator with e on it, I don't know why you would, but you could use like 2.7. It's roughly e. X minus mu squared all over 2 sigma squared, okay? Mu here is the mean value. It is equal to m, our number of things m, times the probability p of our outcome of interest, okay? So this is sort of m number of trials, same as before. P is probability of like interested outcome. Could be 50-50, doesn't have to. This is sort of the total trials again. Sigma in this equation is our standard deviation. The equation for that is the square root of our capital M times probability of our interested outcome. This is a 2 case where we're talking about binomial, so 1 minus p is the probability of the other, whatever the other situation is. Sigma squared or standard deviation squared is called variance. And these two things sort of describe the spread of the points. And so when I was showing you the exam grades, we had a mean, we had how spread was our data around that mean. Okay. And so if you plot probability of x for the Gaussian distribution versus m trials here, so it's going to be centered. It's going to have this sort of shape. Oh, my drawing is rough today. Okay. The curve will always be centered on the mean. This is mu here, the mean. Okay? The mean does not have to be at the center. I'm drawing it sort of in the center of this plot. Depending on what probability is, if it's not 50-50, if it's not nice and even, this curve could be centered off to the side. It could be centered here. Remember, it depends on what p is equal to, where mu would fall, okay? And then what we have is sort of, we can kind of demarcate off regions of plus or minus the standard deviation. We could go even further down to sort of 2 standard deviations away. And so the likelihood of a particular outcome happening, so if it was coin flips and it was a fair number of trials, let's say we flipped a fair coin, 50-50 chance, 1,000 times, m is 1,000, we expect the mean to be 500. And the odds of getting 1,000 heads is all the way over here at what is essentially definitely 0 probability of that happening, okay? So you would have your mean of 500 here, your x would be of getting 1,000 would be located there, okay? And so pretty much about 68% of this whole probability distribution sort of falls within mu plus or minus 1 standard deviation. Oops. And so one of the things you can kind of do when you see a problem is if it asks you, you know, oh, hey, calculate the probability of this, and I think the example problem I'm having coming up, it says the mean is 1,300. What's the probability of getting 1,200? Well, you can quickly use this equation. It'll give you a probability. It gives you m number of trials. You spit out a standard deviation, and you realize you're 2, 3, 4, 5 standard deviations away. Your probability better be a really tiny number, okay? And that's like a good check if you're even close to right, because you know that the number should be really small if you're really far away from your mean.